Have you ever stopped to wonder how a scientist in Tokyo can perfectly replicate an experiment from a lab, say, in Toronto? It's not magic, I promise you. Behind every single number, every equation you see, there's this hidden set of rules, a secret language, really, that prevents total chaos and makes global science even possible. So today, we're going to pull back the curtain and decode that language.
First, to really get why this is so important, we have to go back in time. Because not that long ago, the scientific world was, well, a complete mess. You had different countries, even different labs in the same country, all using their own unique systems of measurement. It was just a recipe for disaster.
I mean, just imagine trying to build something complicated like a satellite when one engineering team is working in feet, another's using meters, and a third is measuring in centimeters. You had all these different systems, CGS, FPS, MKS, all being used at the same time. It was pure chaos. For science to move forward, it desperately needed to get on the same page.
Well, clearly, something had to be done. To fix this huge global headache, the entire scientific community decided to come together and create one single unified language for measurement that everyone could agree on. And that solution is the Système International d'Unités, or as you and I know it, the SI system. Yep, it's the modern metric system. It's this beautifully complete and logical set of units that pretty much the whole world uses for science, for business, for everything. It's basically our universal translator for measurements. And the real genius of the SI system? It's just so simple. Everything, and I mean everything, is based on the power of 10. So converting from, say, grams to kilograms, you just move a decimal point. That's it. No more remembering weird fractions or random numbers. It's just clean, logical, and incredibly efficient.
Okay, so if the SI system is this universal language, what's its alphabet? Well, it all comes down to just 7 fundamental building blocks. We call them the base units. Every other measurement we use is just a combination of these 7. So let's meet them. First up, the meter, the OG unit of distance. It used to be defined by a slice of the Earth's circumference, but now it's tied to something way more fundamental, the speed of light in a vacuum. You can't get much more universal than that.
Next, we've got the kilogram. Now this measures mass, which is the amount of stuff in an object. That's different from weight, which has to do with gravity. For the longest time, the kilogram was literally a metal cylinder locked in a vault in France, but now it's defined by a fundamental constant of nature called the Planck constant.
Then there's time, measured in seconds. You know, for things like GPS to work, we need mind-boggling precision. So we define the second based on the vibrations of a cesium atom. It takes over 9 billion times per second. Wild, right?
For all things electric, we have the ampere, or amp. It's a measure of the flow of electric charge. So, think of it like this. It tells you how much electricity is actually moving through a wire at any given moment.
When it comes to temperature, scientists use Kelvin. Now, unlike Celsius or Fahrenheit, the Kelvin scale starts at the coldest possible temperature in the universe, absolute zero. That's the point where all atomic motion just stops. This makes it perfect for scientific work.
This one's a favorite in chemistry, the mole. See, atoms are ridiculously tiny, and you deal with huge numbers of them. So the mole is kind of like a chemist's dozen. It's just a standardized, gigantic number that lets us count atoms and molecules in a convenient way.
And finally, we have the candela. This one measures how bright a light source is in a particular direction. It's all about the intensity of a single point of light. And that's it. Those are the 7. From just these, we can build almost any other measurement we could ever need.